Well, hello everyone, and thank you for joining me. Soil Vision is proudly in its 20th year and provides geo-innovative modeling software to over 50 countries worldwide. My name is Murray Fredland, and I'm the President and CEO of Soil Vision, and I'm pleased to present today's SVSLOPE Climatic Slope Stability tutorial. And really what this tutorial is used to illustrate the use of a seepage and slope stability model considering the influence of a rainfall event on the resulting factor of safety. The climatic effects are considered over a period of 3 days, and the combination of SVSLOPE and SVFLUX GE are used to model a transient change in pore-water pressure and the resultant changes in the factor of safety for the slope. And this model is based on site data taken from a slope in Hong Kong. And so today we will be using SVSLOPE 2D and 3D. Of course, this can be done in 2 dimensions or 3 dimensions with SVSLOPE 3D. And we're happy to walk you through this tutorial here. We should be noted a place to submit questions and ask them in writing. They appear on my screen, and I will do my best to answer the questions as they come in today. So I'm excited to get going on the tutorial today. What we have on our screen here is I've opened the software, and we are looking at a list of projects and models here. And this is the overall SV Office 5 Manager. So what we're going to do, I've also opened up the tutorial manual, which is just found under the Help menu. If you're following along, you can click Help and open the tutorial manual here on the menu. And the tutorial manual, I've drilled down to SVSLOPE tutorials and then SVFLUX combined, and we're looking at the Hong Kong example in this case today. So this is the one, there's a description of this model, there is a solved model under this project if you want to have a look at it, and you're welcome to follow along with me as mentioned in the tutorial. So let's get going here. Let's just see here. All right, so if we go here, I'll just click on the model setup. Then we have the first steps here. Overall, we should say that this is called a combined model. It's not really fully coupled, but it's combined. It's going to use the SVFLUX package and the SVSLOPE package. And so really you can combine the models, number one, in our software. And really what we're doing is we're going to solve the SVFLUX model first through SVFLUX GE, at which point then we're going to combine the two and enter the SVSLOPE portion and set it to solving the model. So the basic idea is we're going to compute the pore-water pressures and the changes therein, and then what we're going to do is combine and pull in the SVSLOPE software, and it's going to pick up every pore-water pressure snapshot that we've outlined, and it's going to pull it into a limit equilibrium analysis and perform the analysis. So just a quick note, I got a question that's good. What's the difference between combined and coupled? And what we view our terminology is coupled means that there is a back and forth influence on the parameters. So an example of a coupled problem would be consolidation, where you do a change in pore-water pressures, and that affects the deformations, and the deformations in turn affect the pore-water pressures. So there's a back and forth iteration between the partial differential equations in order to iterate and come to a new equilibrium on every time step. When we say combined, what it means is we're just things are going one way, if you can think of it. In other words, we are pulling pore-water pressures from SVFLUX into SVSLOPE, but we're not feeding any data from SVSLOPE back into SVFLUX to affect anything. So hopefully that answers your question there. But great question here. So let's keep going here. We're going to create this model. So the first thing we're going to do is create a new model here. I'm going to click on this project and pull it in here. And then I'm going to click on this button right here that says create a new model. I can also, every button has a corresponding menu option in our software. So we can go up to models. I can also create a new model here. But I'm just going to press the button here. I'm going to create this under SVFLUX GE, which uses the Flux PDE solver. This is a two-dimensional numerical model. It's transient, so I'm going to select transient. We're going to use metric units, days. The end time is 3 days in the tutorial. I'm going to go 6 days just to run this out a little bit more. And we'll call it Hong Kong 01. So there we've set up everything we need to create the numerical model. And I'll click OK. And it's going to go through, and here we have a blank canvas and a place to create our numerical model. So the general idea and the general concept behind our software is that you move from left to right through the menu conditions. So we would set model settings, enter geometry, material properties, then initial conditions if they're there, and boundaries. And then the rest of it is solving and related to solving and graphing results. So any boundary value problem, really you're looking at three things: geometry, material properties, and boundary conditions. And the rest of it is somewhat superficial. So it's very logical. You just go from left to right. So it's quite simple in terms of if you want to just draw a region polygon, you can go in the software. There is snapping. And when you draw a line, it gives you the angle of the line, how long it is, what the horizontal to vertical ratio is of that line. So it's very straightforward to go in with the CAD interface and just draw shapes randomly. And you can set, of course, the snapping and everything else to whatever you want. So that just illustrates the drawing here. We're going to undo that, and we're going to follow the specific tutorial steps through the model here. So what I'm going to do is take this, drag it over to this side of the screen so I can see my tutorial steps as well. And here's the first thing. First thing we're going to do is enter geometry. Shut these off right now, that legend. So this, again, I mentioned there's multiple ways to get geometry into the software. You can import it from AutoCAD, ESRI shape files, other existing models, results of other models. There's a lot of different ways to get it into the software. You can import it from other software packages. And so here what we're going to do is click Geometry, Region Properties, Regions. And what we've got is one region. Now, a region is like, you can potentially have multiple shapes on it, but you can think of it as like a layer in AutoCAD. And we're going to, in this case, have 4 regions. So right at the start, I can either just draw them and it automatically bumps it into 4 regions, or I can click New 3 times, and then I have 4 regions defined here. And just the options are show the region, fill it, show boundaries. So we're going to go region 1. Now we don't have geometry for this, so what I'm going to do for the sake of time in this tutorial is take the region out of the tutorial, region 1 geometry. I can right click on it, hit copy, and then I can paste it in here by hitting properties, new polygon, paste. I've pasted this in there. I can click OK, and I've got a closed polygon. It should be noted, just as a matter of details, that if I paste a polygon that is not closed, the software will automatically close it for you. The rule is that the software must have a closed polygon for every region. So that being said, region number 1 is entered. I can go again now to region 2, and which is not defined currently, and I'm going to go to my tutorial, pick off the points, and copy those into region number 2. new polygon, paste it in, and I've got region 2. And can be seen if I just move my dialog here. As the regions are pasted in, they show up on the CAD control window. So again, going back to my tutorial, there's my 3rd and 4th regions. So I'm going to go over here, pull these data points. Paste those in, and again go to region 4 and paste those data points in. Copy them here, select region 4, new polygon, and click paste, and these points go in. Right, so there, it just shows us in the tutorial that if we've done everything properly, we should have a shape that looks like this, and we do here. And if we click on any, the software is very object-oriented, so if we click on any particular region, it selects it here, and what I can do is either double-click on that region. So if I double-click on this one, it shows me the region properties for that region, along with the display properties and what material is assigned to that region. We don't have materials entered, so there's nothing assigned right now. Or I can right-click and select that region, and I can calculate that area of that region, for example. Or it shows you basically everything that you can do with that region. I can delete it, I can apply a material with it, or I can slice it into subregions. So, or I can assign boundary conditions. So there's a few things we can do with each region. I should just spend a quick moment on selection, because this is important with the software, in that there's multiple selection modes in the software. Right now I'm on the mode where it selects the entire object. I can do an object cell, I can do a line segment selection, or a point selection. So these are handy little features that I find, because they work great for if I want to, if I'm now on line selection mode, now I go over top of a polygon and I select the line, and all of a sudden I can just select that line and I can apply boundary conditions to it. Alternatively, what we get people saying is, oh, I entered a point wrong. I want to move the point. How do I move it? Well, you go to point selection, you can select a certain point and translate it or delete it. So there's nice little ways to move geometry around. If you move a point that is on 2 different regions, it'll move both regions. If sticky is on, if sticky is not on, then it'll just move one at a time. So there's nice features in the software for moving and editing geometry points. So the next thing, we've now entered geometry. Now we're going to go and enter material properties for the seepage model. And so we have a mixture of 4 parameters. 2 of them are unsaturated parameters. In other words, they have a soil water characteristic curve and an unsaturated hydraulic conductivity portion of the curve, and 2 of them are saturated parameters. So if we go through entering those, we can go to, we're just going left to right again. We've just basically did geometry. Now we're moving to materials. We select the manager. And of course, there's no materials entered for this model right now. So we can go new, and we're going to enter the first material called colluvium. And of course, this is an unsaturated model. So we're going to do a saturated volumetric water content right here. Then we are going to enter a Fredlin and Zing fit. So we select that for the unsaturated portion of that. So we're on looking at 2 aspects of these properties for a seepage model. Of course, there's volumetric water content, and there's hydraulic conductivity. So Fredlin and Zing, of course, we've selected the mathematical fit, but there's no parameters right now. And the question is how do we get parameters for this Fredlin and Zing fit? Well, we have a few options. I can pull down, I can enter laboratory data, which is what we're going to do here today because we have laboratory data. I can type in resultant and zinc material parameters, or A, N, and F parameters if I know them. Then there's a series of estimations I can do. Torres estimation, Zapata estimation from Arizona State University, or there's example materials that are classic soils that have been tested. A silt, a sandy silt, Eola-light clay, or Guelph silt, drying, wetting, or superstition sand. So if we pick either of those, we just get default parameters entered for our soil water characteristic curve. However, today, as mentioned, we're going to go through and we have data. So I'm clicking on data. I'm going to go down here in my tutorial a little bit, and here is my SWCC data. I'm going to select that, copy it, paste these points in, and OK. So I've pasted the points in, but I still don't have my fitting parameters. So to correct that, I just click the Apply Fit. It initiates a nonlinear least squared regression algorithm. It takes over and it determines what my parameters are. Now it's determined parameters. It's got an air entry value of 2.64 kPa. Here's your maximum slope. If I graph this, here's what it looks like. Here's our air entry value. Here's the data points. Here's the air entry value construction that's used to determine the air entry value and the wilting point, or the residual suction point. And your blue line is your fit curve. So we've got a good soil water characteristic curve, a decent fit, and we can move on here. R squared is 0.9946, so 1.0 is a perfect fit, so it's fairly decent. So now we need hydraulic conductivity information. We can go down here. If we go up here, our hydraulic conductivity is 2.59 for KSAT, so I'll enter that, 2.59 for KSAT. And we're going to use the modified Campbell estimation technique. And we're going to enter here to click the p-value for that parameter. What we can do is there's a function where you select, in this case we're going to do silty clay, and it says your p-value is 5.59. And then we're going to adjust our minimum here from -10 to -6. Seepage solutions are somewhat sensitive to the minimum conductivity. Any finite element equation has a certain minimum that it can solve reasonably well. And so we're going to reduce that a little bit to -6. And there we have that. So one other thing, we can also graph this to see what our curve looks like. Here's our air entry value. We're coming down on the modified Campbell, a number of orders of magnitude in terms of meters per day, and then hitting the minimum and smoothing off at the minimum. It should be noted that every minimum or every soil property has a reasonable minimum at the vapor diffusion limit for a soil, and it's good not to go below that, or the solution becomes a little bit unreasonable. So we've entered our colluvium material. Now we can keep going through this. There's steps here you can try to follow if you're following along, or we will just enter them here. Weathered granite. And this is again unsaturated. Now we have a volumetric water content 0.4. We're going to enter that there. And we're going to use the Fredlin and Zing fit again. Go to properties. For this one, I believe we have data here. Weathered granite saltwater characteristic curve data is here. Copy that in there, paste it again, and then apply the fit. Same procedure as last time. And we've got parameters, and we can graph them. And here's the updated parameters. Here's our fit, and again, we get a good, decent fit. Okay, hydraulic conductivity for this material. Go back to my tutorial. It's 0.61. And we're going to use modified Campbell estimation. Go to the properties, and again, we're going to pick silty clay. as our parameter, and it determines a P parameter of 5.59. If we want to graph that again, here is our unsaturated curve for that material. So there we have two parameters defined. The next two are going to be a little simpler because they're just saturated materials. This is less weathered zone, saturated material. KSAT in this case is 0.52. Volumetric water content is 0.4. And bedrock material. Saturated material, KSAT is 0.43. 0.4. And we have all of our material properties defined. So we've got them defined here now, but they're not applied to any soil regions, because once they're applied to a soil region, then that region is colored, the color of that region. Just had a quick question here. I'll go back to this here. I had a question. What is the maximum slope? I think that was reviewed down here. Maximum slope is a measure of the slope of the SWCC at the maximum point of slope right around here, is what that is. So that's a measure of how fast the material is drying, or how fast water is leaving the material as suction increases. So what's happening in the soil here is it's saturated out here, and then what we're applying in the soil is increased tension in the water phase, or suction. So as we're applying that, at first there's less change. Then all of a sudden we hit past the air entry value, and the change rate becomes more rapid, up to a maximum up around here. And then the rate of change slows up out through here, and as you're able to pull less water from the smaller pores. So the air entry value and just afterwards is typically the zone of largest desaturation. In other words, the larger pores are emptying in the soil. So hopefully that explains what that is. So it's more just a representative of how fast the water is able to be taken out of the soil after the air entry value is exceeded. So we have all of our material properties entered here. The tutorial lists some hydraulic conductivity values, but we're estimating them with the modified Campbell, so we don't really need to, we can enter them just for the sake of an interesting comparison, but they don't affect the analysis at all, so I'm leaving them out purposely. So we need to assign materials to regions. So there's a number of different ways to do that. I can go here, and here's my mapping. It says region 1 is colluvium. Well, here's region 1. If I click on them, it says here's what my region is. Here's region 2. So region 1, it says is colluvium. So there's a few different ways I can do this. I can just right-click, apply material, colluvium, done. Or I can go in through here, select all my regions, and just say here's region 2 is weathered granite. Region 3 is less weathered granite. Region 4 is bedrock. And there we go. So now we have all of our materials. So color in our software is associated with material. So if your model has a color, it means that there is a material property assigned to that region, is what we're indicating in the software. So it's a good visual cue of what materials are assigned to what region. And here is a legend I should just mention that is a floating legend. The user can move it anywhere they want. It shows the KSAT and the porosity of these materials. And if you just click the X in the upper right corner, that legend disappears. So the user can move it wherever they want, or they can get rid of it entirely. So now what we want to do is specify an initial water table, and that's under initial conditions. Go here, initial head, And in this case, it's by default, the variable, I mean, there's a few different options. You can set initial conditions globally or per region. We're selecting them globally right now, and we're selecting them as head values. You can also do pore-water pressures. We're doing heads. And what we're going to do is, rather than pulling them in from another SVFlux analysis, we're going to pull them in based on a water table. So here's our water table. There's a few minor settings we're just going to leave as the default. So we've selected to put in a water table. So again, we go into here, initial conditions. Now all of a sudden the initial water table is available, open and available for entry. So we're going to click there, and we're going to set the initial water table at the points, just like in the tutorial, at 0, 15, and 110, 15. So initial water table of 15 meters. And it shows up here on our numerical model. So just moving again left to right, we've done geometry, materials, initial conditions, and now we want to do boundaries. So how do we set boundary conditions? So really the flow on this model, the general rule of thumb for most seepage models is that really there has to be a place where water can enter and a place where water can exit. And so here in this model, what we're doing is we're raining on the top of this model, on the top of the slope, and then we have to allow it to exit somewhere. So we're going to put a head boundary condition right along here that allows water to flow out to the right. And we're going to keep the bottom and the left hand conditions no flow. So firstly, we need to define our climatic condition here. And that's where SVFlux really starts to shine, in that they have a climate manager. So we're going to go into the climate manager, pull it up here, and we're going to do a new boundary condition, call it rainfall. And we can define, there's different areas. The software can take into account, for example, precipitation, evaporation, or transpiration due to plant boundary conditions. So those are different things that the software is capable of handling. In this case, we're going to keep it fairly simple. We're just going to enter precipitation in this case. So we click on this, precipitation, and we're going to include precipitation in this one, and then we're going to enter a rainfall event, time 0. We're going to enter, or day is 0, we're going to enter a flux of 0.05. 1 and 0 flow on 0 rainfall on day 1, and 2, 0 rainfall again. So we have more days entering the model. It'll just keep extending this, or we can do day 3, 0, 4, and 5 as well. So this rainfall event has an intensity that we have to specify. So what we've done is we've set all data as global intensity. So in other words, every rainfall event has the same intensity. And by intensity, we mean kind of what is the, when we specify a flux of 0.05, does that happen over the entire day, 24-hour periods, or is that a huge rainfall just within a half hour? So that's what intensity defines. So in this case, we're saying that, well, there's only one rainfall event, so we're going to start it at, let's see here, what's our dialogue, say our tutorial, 8 hours and 14 hours. So 8 hours it's going to start, and at 14 hours it's going to end. And it's going to be parabolic, so we can make it trapezoidal or parabolic as well. So we've got one event right at the start. If we want to graph that, this is kind of what it looks like. We've got one event, the start here, all of a sudden it ramps up. Here's the parabolic event, rainfall event of water being added, and then there's nothing here. So we're looking at the effects of this one event on the slope stability is ultimately what we're looking for. So we've entered this here now, this climatic boundary condition. Now we have to apply it to the upper slope on this on this model. So there's a few ways I can select this, and I can go boundaries and boundary conditions, and you can see as I click on different boundary segments, I can assign a boundary condition. That's one way to do it, and I just click that I want a boundary condition of climate here. And where is it here? Down. Oh, there it is. Up a little bit. Climate and rainfall. And I'm applying that there. And then I'm saying on this one, I'm going to say just continue that same boundary condition. Same one here. Just continue it. And down here, then continue it. So then I've applied it, and you can see little graphic symbols are added to show that we've applied that boundary condition to there. So that's methodology number one. I can also just go in here, and now I'm selecting every object, but here's where the object selections become very useful to me. What I can do is select a line segment, and I can select a line segment, but I want to select multiples of these and apply the same boundary condition to them. So what I can do is hold down my control key and select multiple boundary line segments, and then right click, and I'm applying the climate boundary condition, and I set that equal to rainfall, which is what I called it before. So there's that boundary condition applied. So two different ways to apply boundary conditions in the model is what we wanted to convey to you today. The next thing we need to do is apply the boundary condition on the right. So again, the easiest way is to just do a head constant. And the tutorial says 10. I'm actually going to keep it the same as my initial water table. So a little bit better posing of this, so there's not a difference between initial conditions and your boundary conditions. That's something you should watch for in a numerical model. We get a lot of models through tech support where the boundary conditions are vastly different from initial conditions, and it creates a lot of oscillation and convergence problems potentially right on the first few time steps where the model tries to resolve the difference between the initial conditions and the boundary conditions. So a short rule of thumb is keep your boundary conditions similar to your initial conditions in your numerical model. So we're applying that. Here's our boundary conditions applied there, and here's our model, which roughly looks the same as the screen. We just got a slightly different color scheme going there. So we're going to adjust a few FEM options when we get over here. Here's the finite element options. We're just going to decrease the initial increment, 0.1, the maximum increment, 0.2. This just limits the solver to not taking too big a time steps moving forward so that you don't miss a climatic event or a jump too big, too far in the transient analysis time step. So we've got that. Now, the next step is we're going to combine SVSLOPE with SVFLUX GE. So I'm going to save this model, just clicking the Save button, and then I'm going to combine it like we talked about before. And I just do that through the model, add or remove coupling. So that's a fairly straightforward step. And we're just going in here and we're going to say here's what's available to couple to this. So I'm going to couple in SVSLOPE, move it over to here. And now it's going to say, well, I just want to save this coupled model as a new file, which I'm okay. So I can just give it a description, coupled or combined numerical model. Okay. I just got a question. What about the left-hand boundary? In this case, we're just leaving it as no flow, right? So if we don't assign anything, and it's a good point to mention, if we don't assign anything in the software, it's automatically by default treated as a no flow. We're free to, if we had instrument readings or piezometer values from the left-hand side of the model, we could assign those and put them in. And I believe the original site had a few more piezometers installed into it, and there was a general left to right flow that was background levels in the model. However, we're just not getting that detailed for this tutorial. We're trying to simplify it a little bit. But there's nothing stopping you from the user as assigning a head boundary to the left-hand side of the model as well, and that's perfectly all right. Okay, so now we've coupled the model, and we've got, you'll notice now the SVSLOPE icon appeared here, which means now we can flip back and forth between SVFLUX. We're currently in the SVFLUX software as shown by the icon and the wording up here. Now we can do SVSLOPE, but before we do that, we're going to analyze this model. I'm going to save it, and we're going to analyze this model. And during the solution, you can see it meshed it up automatically. There is automatic mesh refinement in the solution. It's applying boundary conditions and running the numerical model here going forward. And there it's done. So these are graphs in the software that you can see during the model solution. So one of the criticisms of typical software is, well, it's a black box. Well, actually you can see everything that in terms of all variables at any point in time or space in the solution itself. So you can get a much better idea of what is the solution for this model. So we've solved that. Now if we want to see the results in detail, we can click on Open AccuMesh. And what that does is it shows us here in terms of pore water pressure what's happening in the model. So this is time 6. I go back to time 0. Here's my pore water pressures, and the brown is I mean, it's just a color scheme. We can change it to pastels if we want, just for visualizations, but we're going to leave it as unsaturated and saturated. It's just somewhat helpful in this case. And if you look here, all of a sudden you're seeing what's interesting is time 1, which is right just after the first rainfall event has happened. You can see that the rainfall has two things. It's been applied to the boundary, and what's nice here is you're seeing automatic mesh refinement kick in along the boundary to improve the quality of your solution. Because this is where the action is taking place in the model. We're applying a flux and we're loading the numerical model, so to speak, with a flow, and therefore you need a little bit extra mesh density along the upper surface. So we can see that happening automatically in the solver here. And that's one of the nice features of running with FlexPD is there's automatic mesh refinement, and it handles that for you. We got a question here. Can you start your model in slope and then couple to flux, or do you have to start in flux? Great question, and it actually doesn't matter which you do. You can do it either way. You can start a slope model, add in SVFlux, or the other way around. We're just doing this for illustration. Today it's starting in SVFlux and then adding slope, but it doesn't matter in the software. So if you select different times, you can again see the dissipation of pore water pressures, or you can change your variable to plot heads, total heads. And in this case, you see a little bit more dramatic. Here's your initial model with heads, and all of a sudden you're getting impact of the rainfall on the upper boundary condition. And you can see then as the water stops being added, dissipation of the water pressures over time. And if we ran this model long enough, it would kind of go back to a steady state condition. So here we can look at this, get the pore water pressures, get a good idea of that. So if I go back to SVFlux, there's the front end. We keep going through our tutorial. Now really what we're focusing on is adding in the slope stability portion of it. So all we do to do that, we've added in the slope part. It's there. I just click on this icon, and now I'm in SVSLOPE. And here's all my material properties. That just assigns default parameters to all of them, but it keeps them all named the same and the same colors. So first of all, again, our paradigm just moving left to right. What we can do is go in here, settings, and we want this to be left to right, i.e. the slip is going to be this direction. Circular slip surface. we're going to change this up a little bit. Rather than doing entry and exit, we're going to do a slope search. And we're going to do, we'll do 1,000 slip surfaces here on each one. So then on the calculation methods, here's all the different calculation methods. We're going to use GLE. We're going to change up the lambda value a little bit here. We're going to start it at 0 and go to 0.3. And it's about 10 increments, generate that. Here's our lambda values. And we're okay with everything there. So we still need to correct for the material properties though. We've added in, it's by default selected these parameters. So we're going to update them. So here again, moving left to right, we've got geometry already, material properties manager. We're going to go in here and we want to, right now this is a more Coulomb strength constitutive model. So what we're going to do is we want to change it to account for unsaturated strengths, because the problem here in this model is that if we just ran more Coulomb does not consider suctions, the effect of suctions. So if you ran the model with more Coulomb strength, you would see no influence of the changes in suctions up near the ground surface. So to include the impact of suctions on shear strength, you need an unsaturated constitutive model. So the way I do that is I can select colluvium, and I'm going to have to change this, and I can change this strength model to any other model in the software. Here's all the soil models, strength models, then there's rock strength, and then here's a whole bunch of unsaturated soils models. We're going to pick 5B, like that, and really just enter our parameters here. Now, so cohesion is 10 kPa, 35 I don't need to change, and my friction angle for 5B is 10 degrees. So in other words, what you have to remember with this strength method is if you set 5B equal to 35, what you're saying is that the increase in strength due to added suction is the same as the increased strength due to a net normal stress. And in different soils, it depends on what levels of saturation they are, but that's generally not, this would be the upper bound case. So generally what we take is 5B as a fraction of the regular friction angle. In this case, we're making it 10 degrees. And make this 19.6. It's close there, but we're going to increase that. There we go. So we can go through these again. Weathered granite, we're needing to update that to 5B. Go here, select unsaturated soil, click OK, and update those parameters. So here's cohesion is 15.1, 35.2, and in this case 10 degrees. And unit weight 19.6. Less weathered zone, again, change method. We're going to go to 5B, change this over, and here's our parameters. 23.5 is the cohesion, kPa, 41.5, and 10 degrees for friction angle, and 19.6. Bedrock, we've got as more Coulomb material. However, we have an actual bedrock material in our software in SVSLOPE, so we're going to switch it to that here. Bedrock. There we go. Click OK, and there we have it. Now all of our materials have been upgraded to consider unsaturated suctions in terms of shear strength, and they're all still assigned to the same material zones, so we don't need to change anything there. So the next section is about specifying search method geometry. With slope search, we don't need to do that, so we're going to skip over that portion of it. Normally we would do that here. You can set the slope limits. However, we have an automatic algorithm that picks the slope limits, and it's already assigned them at the edges of the problem. You can, of course, put tension cracks on the model if you want. So now we get to the interesting part of, well, where do we get our pore water pressures? So if we go to pore water here, we're selecting, it's by default in a coupled model, it already kind of knows that you're running a seepage model, and therefore it pulls the time steps you've imported from the seepage model. And what we've specified to output is times at 0, 1, 2, 3, up to 6 days. And currently all of them are selected to analyze. So we could pull it back and we can do every second pore water pressure snapshot, or every one, or we can pick select ones to analyze. We're just going to leave it at all of them. So we're analyzing every snapshot at every end of every day that we've, at the start and end of every day that we've specified there. So we've now specified the pore water pressures, and now we can go through, we'll save it, analyze the model. It says yes, save and continue. And here it goes. Slope search, day 1, 0 of 6, and it's got about 1,000 trials there. Here you can see the factor safety changing. It's day 2 of 6, 3 of 6. The software uses parallel computing. It should be mentioned, by the way, just to speed up calculations, and as a result very fast on solving these models. The same thing can all be done, of course, in 3 dimensions, as we have a 3-dimensional seepage program and 3-dimensional slope stability. So here we're done, it's finished. You can just click here to review the results in AccuMesh. And here we'll just zoom in here a little bit. Here shows our factor safety. You can, of course, present total weight and all that kind of stuff in there as well. I'll just turn off some of these legends here. So you can show different time steps with different slip surfaces, what it found, different slip for different days. See what it found here. And you can drill down on any of these particular models. You can have an examination of, if I want to show, for example, all the critical slip surfaces that were tried at that time. This shows the 10 lowest ones that were tried. I can say all valid slip surfaces. There's all valid slip surfaces that were tried in this numerical model. And as a result of the slope search, it found them. So like the 10 lowest. You can also, as a note under the slip surfaces, by the way, you can list them. They're listed in lowest to highest factor safety. So if I just click on one of these, it shows me on the screen what that factor safety was and what its location was. Clear that, cancel that. And then you can go in here and graph factor safety versus time. Here you're seeing it, the effect of the rainfall decreasing the factor of safety. And what we should do over time is increase the number of time steps that are analyzed to every like 0.1 of a day, and increase this so you get a little smoother curve that shows you what's happening at each time step. But you can see the overall trend in the factor of safety versus time with this numerical model. So we're done the tutorial here. I'm happy to answer any questions. Now, one question here. Let's see here. Can you input SVFlux into SVSolid to do a shear strength reduction method? Yes, you can pull in pore water pressures into SVSolid to do a shear strength reduction method in the software. And so that's another method of doing finite element slope stability. If you are interested in that, what you can do, let's see here. If you go into your project manager and we do an advanced search and we pull up SVSLOPE GT models. Here's a bunch of SSR models that you can solve and have a look at, and that gets into finite element slope stability if you want to do that. One question is, why is the critical slip surface on day 2 is smaller compared to the others? That's a result of the resolution that we've analyzed at. We ran one model ahead of time here, and if you pick a finer resolution on the pore water pressure changes, you don't get that for some reason. So it's just a matter of the resolution that you pick for the pore water pressure changes versus time. And you have to also make sure that your algorithm is fine enough to detect the critical slip surface at that particular time step. So you might have to increase the number of trials on any particular step. We're making it run faster and reducing the number of trials just to get through it in the tutorial. But if you increase the number of steps with the pore water pressures and the number of trial slip surfaces, your trend gets smoother and better in this model. So that hopefully answers your question there. Any other further questions related to the software? I know it takes a little while to type out questions. Our sales team is happy to help you with trials of the software. We have 2-week trials. If you're interested and want to give the software a try to see if it applies to your project, we're happy to answer questions for you, and we're happy to give you trial versions to help you understand the functionality of the software. Again, there are lots of tutorials with the software. We just covered one today. There's many different trials for individually for SVFLUX. If I go to GE, there's many different tutorials in 1D, 2D, and 3D to walk through with the software and learn to use it. Plus, we have many videos and instructional kind of tutorials that are available on our YouTube channel as well. Let's just see here. There's one last question regarding statistical analysis using unsaturated soil parameters that I will handle offline here, and I will email you after the course here. But thank you, great question here. Yeah, I'm just deferring that because it's a little complicated to answer. So thank you so much for your time, and I've really appreciated it. Thank you for the interest in our software, and let us know how we might be of service to you and your organization going forward. Thank you so much.